equal to plus C is equal to 0. Right, how to solve for x? You can solve it analytically, you have to solve it numerically, and there's a mathematical tool that's called Newton-Raphson method that helps you to solve this x. So I need to double check with Glasgow again, how serious are they on that question. So while I check that out, I plan to discuss the second question of your convection review question. So in this question, you have this pipe over here. Is having a fluid that's heated from 15 degrees Celsius to 65 degrees Celsius. And this pipe has an internal diameter of 3 centimeters and is 5 meters long, right, this tube of pipe. So there is an electric resistance heater at the outer side such that there is a constant heat flux. Right? And heat flux is represented by your Q dot over there. Heat flux means that the amount of heat transferred per unit surface area. Okay? So the units for that will be watts per meter squared. Did you have this question? No, it's in Moodle actually. Okay, you can download it in Moodle. If you don't have that question, that's fine, because I walked through this, and then you just use a separate sheet of paper, or if you have at the end of your lecture notes. For example, I have a blank page at the end of it. You can write it there, or write it separately, and then go back home, print it out, and put it together. So, the outer surface of the heater is very well insulated, so it's applying heat, and all the heat is going radially into this tube. And the system provides hot water at a flow rate of 10 liters per minute. Right, so later on, we need to do some conversion. Determine the power rating of the resistance heater, meaning when you find out is this value, and estimate the inner surface temperature of the tube and the exit. So let's have a look at some of these properties. Some of you want to take pictures. It's in model. Or you want something here that you want to take? Anyway, look it up in Moodle. So I want to solve this bulk mean temperature. I made a mistake for bulk mean temperature. Let me bring it back. Could you see this graph here that I was talking about? Do you remember this graph here? This one should be a plus, not a minus. Did somebody sense that? Yeah. You know, yeah? No, you don't. This is your bulk fluid temperature. So TE plus TI. Please, if you have written down as minus, please put as plus. Okay. Okay, coming back. So let's have a look at this question. By the way, this question is relating to convection. The review questions it means to discuss with you before your exam. Because over in Glasgow they have tutorial sessions, but Singapore side don't have. So I'm including it into the lecture so that you are not disadvantaged. Make sure you practice your tutorial because they are very, very useful for you to refresh the concepts. Okay. So this valve mean temperature, TD, will be your inlet temperature minus plus the outlet temperature divided by 2. So that's 40 degrees Celsius. And we're going to make use of this valve fluid temperature to figure out all the properties of the water. So the following are the properties of the water. And again, if you wonder where are the properties of the water, for Holman, that one is in table A9. Right? A here refers to the appendix. So A9, that's your fluid properties for water. And you're able to figure all these numbers out, but Holman, various textbooks would have slightly different numbers. So if you refer to Holman, you may not be having all these numbers exactly. It doesn't matter. I'll be following using these numbers that are provided for you with this table. So we'll start by looking at the cross-sectional and the heat transfer surface area. So that one will be AC. AC will be 1/4 pi d squared. Right, that's your cross-sectional area. Cross, not surface. Cross-sectional area of the pipe. So if you're wondering how I got this formula, it's actually just pi r squared. It's the same pi r squared, where r will be the radius of your pipe. If I express it in diameter, so I get this form. So this one will be equal to 1/4 pi 0.03 meters squared. That will be equal to 7.069 constant power minus 4 meters squared. So that is your cross-sectional area. Later on, we'll be making use of surface area. And this surface area refers to the wetted surface of the pipe. That is your surface area. Why I need that? That's because it's where heat is going to be transferred radially into your pipe. So that surface area will be something that we need to find out. So that surface area would be equal to pi d multiplied by L. Right? If you think about it, pi d is equal to 2 pi r. That's the circumference of the circle. And then multiplied by the length. That is your surface area. Okay. Some students find it hard to imagine why you say that is the circumference and multiplied by length that will give you surface area. If you can't figure it out, maybe you can approach me. So this equal to pi multiplied by 0.03 multiplied by 5. That's 0.471 meters squared. Now you're given the volumetric flow rate, and the symbol for that is V dot. Volumetric flow rate is given to you as 10 liters per minute. I'm going to change that into meter cube per minute. So this is actually equal to 0.01 meter cube per minute. Because 1 liter is equal to, you got to divide that by 1,000. So 1 liter, converting that into meter cube. So we are also interested to find out what is mass flow rate. That's equal to the density multiplied by your volumetric flow rate. So that will be equal to 992.1 multiplied by 0.01. That will be equal to 9.921. That is kilograms per minute. Convert that into kilograms per second, 0.1654 kilograms per second. Now, for those of you who have done your practical lab experiments already, who have experiences units conversion, just to highlight one thing, there's this safety rule for your lab, which says that you need to wear covered shoes to go for a lab. So please do that, because we're dealing with hot water. It's possible that there might be vents coming out and then you burn yourself with clothes. So please wear covered shoes. So next thing I want to find out will be your Q dot, m dot Cp multiplied by Te minus Ti. Right? That's the flow rate that's going through the pipe. So I have the flow rate already, it's 0.1654. Specific capacity, that one would be, is that right? $4,179 multiplied by 65 minus 15. That one would get you 34.6 kilowatts. So this is a power rating of the heater, because the heater needs to supply this amount of energy or power in order to heat up the water that's flowing within it. So we could make use of that in the following equation. I want to find out what is my Q dot. And actually Q dot is equal to Q. It's a new symbol. It's not, this is Q. Divided by 8. So this Q dot is equal to H multiplied by Ts minus Tm. So how this Tm came about, that's because as I was talking about that pipe, you have fluid that's flowing in, and in this case, heat is transferring in. So the amount of heat that's transferring in must be the amount of heat that's gained when the fluid flows from this point to that point, because the heat is transferring into this fluid as it flows along. So we'll be looking at this boundary layer, and within this has the convection heat transfer coefficient H. There will be a surface temperature that is called Tx, and then the mean temperature that is called Tm. This mean temperature resides in the core of your pipe. Right? So we could re-express this with Ts as a subject. That will give us Tm plus Q dot divided by H. And later on, we will make use of that. If you're wondering what is Tm, Tm is actually defined as the mean temperature of the fluid at this, the core of the tube or the pipe. So we could figure out this Q dot from the following form. Q dot is equal to Q divided by surface area. And we found out that dq is 34.6 divided by that surface area, which was also something that we found just now, 0.471. Work that out, that will give us 73.46 kilowatt per meter square. So you can see the units there already. Kilowatts per meter square. That tells me that that is my heat flux. That's the definition of heat flux. So next thing is to find out what is my average velocity. So I'm going to represent the average velocity in the following way. Capital V, subscript A, B, G for my average velocity. And I need this because I'm going to use it to figure out if the flow is turbulent or laminar. So this is a topic of convection, so you need that. So this equal to B dot divided by AC. That's how you're going to find out what is your average velocity. B dot is what we have calculated previously, that is 0.010 divided by your cross-sectional area, not surface, cross-sectional area, because it relates to the flow. So that's 7.069 times 10 to the power minus 4. If you do the calculation, you get 14.15, but the unit of this is meter per minute. Change that into meters per second. That's your velocity. So with the velocity, we could then figure out what is the Reynolds number. The Reynolds number would be equal to velocity, and in this case, your average velocity multiplied by diameter divided by nu, right? Your kinematic viscosity. And this nu is actually given in the table right at the top of the question. So take that value, put them all together, 0.236 multiplied by 0.03, that's your diameter, divide by 0.658 times 10 to the power minus 6. That will give us slightly over 10,000. Now what does that tell you? Is it turbulent, laminar? That one is greater than 10,000. So it implies that it's a turbulent flow. Once you know that it's turbulent flow, you will use the correct form of Nusselt number. Before I go into Nusselt number, I want to talk a little bit about the flow that is turbulent and the entry length. I want to figure out the entry length. The entry length to the tube is given by LH, which is a hydraulic length, is equal to LT sub T, that is about 10 of your diameter. So that is your hydraulic length for the entry side. And we want to make sure that is it going to be fully developed at your entrance of your flow. And how do we know that? We take that value as 10 times of your diameter and then check that out. Where is that point? What I mean is that this number, that is 0.3 meter, that is your entry length. So if you look at this entry length for the pipe length, that is 5 meters. So your pipe length, that is 5 meters over here. And 0.3 meters is sort of like a very tiny section. So this is the part that will come in and look in that way. Right? And then you have all your fully developed flow over there. So you can see that most part of your pipe is actually fully developed flow. And that's why we need to be sure about that. So this LH is much shorter than the total length. Total length of the tube. So that's why we could assume that is fully developed turbulent flow. Okay. So with that, then we could figure out what is our Nusselt number. That one is equal to HD divided by K. And we're going to make use of of the Nusselt number that is 0.023 RE PR in that way. So we can start to substitute it inside. So that will be equal to the following 10760 to the power 0.8. And the Prandtl number that was right up in the table, that's 4.32. And equal to 69.4. So once we have the Nusselt number, we can figure out what is our convection heat transfer coefficient, 8. So that one is equal to the following form, just readjusting this Nusselt number expression. Is 0.631 divided by diameter multiplied by Nusselt number. Work that one out, 1460 watts per meter square degree Celsius. So just now we saw that Ts can be expressed as Tm plus Q dot divided by H. It was the H that was missing, so now we have calculated that. We can put it in. Tm here, 65 degrees Celsius. So the Tm there, I'm going to assume it as your exit temperature, right? Your exit temperature, Tm. So that's 65 plus your Q dot, which was what we found just now, 73460, divided by the H that we just calculated. Work that one out, 115 degrees Celsius. So that is the surface temperature of the pipe that's been heated up, and that heats up the fluid that's flowing within it. So just something to note, yeah? A small little sentence. Now note that the inner surface temperature of the tube is actually going to be 50 degrees Celsius higher than the mean water temperature. At the tube exit. So this temperature difference would maintain to be constant throughout the fully developed fluid. So the temperature difference of 50 degrees Celsius between the water and the surface and that surface refers to the tube surface. It will remain constant throughout the flow that is fully developed flow. Just a small little side note so that you could take a step back and have a look. Yeah, the temperature difference is going to be kind of like 50 degrees Celsius. Difference between the water and the tube surface. So please attend your 2 tutorials. Actually, for your conduction and radiation, the tutorial has been posted up already, which is very, very little question. So I was asking last year, are you going to be giving more opportunities to practice? It seems that they don't have more than that. what I'll advise is that you could look at some positive papers, but don't look at papers that are too far away. Right? Typically 2 years gold paper. The further away you look at, the